So let's go for the second part of the alkynes is the properties of alkynes. In the properties of alkynes, let us see some points of general points. General points let us discuss and then go for the individual properties of the alkynes. As we have seen in the alkanes, the CC bond is non-polar and the molecules will not have any delta plus or delta minus charge. So, the molecules are said to be neutral. The molecule is highly neutral it is. And when there is a sigma bond attached with a pi bond, then this pi bond is formed out of what? This unhybridized orbital sidewise overlap. So, therefore, they are considered to be electron rich. In fact, there is no minus charge on the alkenes, but the way the electrons binded to the carbon is loose. So, that is weakly binded. So, therefore, any reagent which can want an electron or electrophiles specifically can attack and open the pi bond and get the electron. So, they are source for the electron. Electron donors are nothing but the bases. So, therefore, the compound is basic in nature. So, alkenes are basic in nature. Now, coming to the triple bond. Triple bond is having the two pi bonds in fact, isn't it? So, one pi bond will be on the y axis, another pi bond will be on the z axis. So, two pi bonds means what you expect. Expected property should be more basic in fact, because two pi bonds are there, one pi bond is basic, two pi bonds should be the more basic. But what is found? Found is not like this more basic, but it is found one property, it is not that basic, it is less basic only. Not more basic, less basic only. Why it is less basic means, as if you see the carbon, that is S percentage and the P percentage, if you see, this is sp3 hybridization, S percentage is 25%. Here it is sp2 carbons are used, so S percentage is 33% is there. In the sp hybridization, S percentage is 50. So, as the S percentage increases, S orbital is spherical and the more or less the electron density is closer to the nucleus. That is the feature of the S orbital. And as the S percentage increases, the orbital length decreases, overlapping capacity increases, that is what stronger bond formation feature increases. So, thereby what happens? There are two pi bonds are there because of the more electronegativity, sp carbon, because of the 50%, the carbons are found to be slightly more electronegative than the so called sp3 and the sp. Because of this electronegativity, increased electronegativity, the pi orbital electrons are more, they are attracted by the carbon. So, therefore, the cloud, no doubt here 2 pi electrons, here 4 pi electrons, but the 4 pi electrons come closer. So, this bond found to be a shrunken or the orbital cloud, it will be more fluffy, but here the orbitals are coming closer and will be packed type of the observation you find. That means an electrophile will find a difficulty in taking these electrons. So, they are less electron the donating capacity. That is why I said it is less basic. This less basic is explained by the sp hybridization or 50% S character, or in the other way more electronegativity of the carbon holding the electrons tightly. So, the electron donating capacity is slightly decreased, therefore, the basicity instead of I expected more basic found to be less basic. This is the reason. And moreover, there is another point. The hydrogens attached to the carbon here and first and second cases many times break in the center and the hydrogens are given out as the H dots, that is free radical type of reactions are expected in the alkanes. But as you come down from the alkane to alkene to alkyne, because of the electronegativity, the electrons are more pulled toward the carbon. No doubt the bond becomes strong, because as the electronegativity increases, bonds will become strong. So, the bond will become strong, but unfortunately the too much the pulling of the carbon, bond breaks unevenly This type of breakage is called heterolytic fission. This heterolytic fission leads to give the acetylene into minus charge and the hydrogen into plus charge. This type of breakage you may find. This breakage is called what? Uneven type. So, minus plus, that is heterolytic or heterolysis taking place, and then H plus is coming. So, we know the definition, all H plus donors are therefore found to be acidic. So, therefore, the second quality is acidic quality is also developed now. They are not much basic, less basic is there, but acidic is there. So, in fact, basic is there, acidic is there, a compound both are same quality, equal acidic and basic, we may say amphoteric. But in this case, basic, acidic is there. Basic you can find, you add HCl, you can verify HCl is added. So, HCl means acid is adding, means it is base, no doubt. But it gives a proton. Just now we have seen sodium metal reacts, metal is in a base. With that base it is reacting, means this is giving a proton, and therefore it is acid also. So, two qualities are there, net is actually acidic only. It is not equally acidic and basic, slight acidic quality. To the pH paper it shows blue turns into red, means slightly acidic quality is dominating over the basic quality. So, therefore, if a straightforward question, alkanes are neutral, alkynes are acidic in nature. Okay. So, this more basic is gone, totally acidic has come. So, the alkanes are neutral, alkenes are basic, alkynes are acidic, provided this hydrogen should be there attached to this one. Therefore, if you have a specific example like a butane containing hydrogen, a butane not having the hydrogen attached to the triple bond. Here hydrogens are there, but what type of hydrogen they are? They are alkane hydrogens. There is no hydrogen directly attached. So, this the first compound only acidic in nature, second compound in fact basic in nature. Okay, because of the triple bond presence it shows basic nature. This is basic and acidic, acidic is dominating because of the hydrogen attached. Heterolytic fission leads to give the H plus. There is no heterolytic fission here because H is not directly attached to the sp carbon, but it is attached to the sp3 carbon. Therefore, this is fundamentally 2-butane is basic in nature, 1-butane is acidic in nature. That is the point. So, ultimately what we say is this 50% S character are more electronegativity, or so I will repeat once again, sp hybridization or 50% S character or more electronegative nature, is resulting in the so and so points. The first one is less basic, isn't it? Second point is they are acidic also, provided if that hydrogen is attached. Third one is less towards electrophilic addition reaction. As I said, electrons are tightly held, so electrophilic addition reactions will be slow. Imagine that, take an example, you take acetylene and ethylene, add bromine. Ethylene completes the bromination fastly than the alkyne, because though the alkyne is having 2 pi bonds, the electrons are tightly held. So, electrophile attacking on alkene is more. So, ene is more reactive or more towards, our electron donating properties are more in the alkynes than. So, less reactive towards electrophilic addition. So, let us say 10% electrophilic addition decreased. Then what that 10% gap will be filled by the some nucleophilic addition reactions also takes place. This is the another special property. So, alkynes undergo nucleophilic addition with, especially with HCN and the methanol. 2 examples are there. And also oxidation, polymerization, all these reactions also, they are always taking place slowly reaction. Okay. So, electrophilic addition less, some nucleophilic additions takes place, the acidic property and the reactivity is less reactive than the alkynes, and this hydrogen is acidic. So, therefore, due to this acidic they react with metal. So, you can say metal derivative formation. metal derivative formation. This is also one consequence of the sp hybridization. So, therefore, the compound behaves this in the place of hydrogen some metals are coming. So, these metal derivatives are just now we have seen used in the conversion of alkynes to other alkynes, and similarly especially with silver acetylide and the copper acetylide, they are white and red colored, therefore, in the differentiating reactions also we are able to use. So, all these consequences are because of this sp hybridization. Now, let us go one after the one. We will see that the what type of reactions alkynes undergo. So, let us take the first property as a electrophilic addition reaction. Electrophilic addition reactions. As we know, the ethylene reacts with HCl, it will get the ethyl chloride. Similar to that, acetylene also undergoes several electrophilic additions. The simplest addition with HX, let us take example HCl, HBr, HI and so on. All these hydrogen halides can be added. So, let us take HCl is added. So, one side H plus, the other side Cl is added following the same norms of electrophilic addition reaction. HCl is an acid, so therefore, does not require any catalyst. H one side you get a carbocation on which Cl minus. Step 1 will be always electrophile will be added and followed by nucleophile. So, the reaction you will get. Now, this vinyl chloride has a resonance stability, therefore, second reaction will be slightly slow takes place, but still HCl adds following the Markovnikov rule also. What is that rule? Whenever HX is added, X minus will be added where number of hydrogen, that means this side hydrogen. So, second mole of addition of HCl, if I take Cl goes to this side only. So, you will get the 2 Cls one side adjustment. This side you will get 3 hydrogens. This is once again, if H is added here, you get an intermediate like this. H is added here, isn't it, on the triple bond. One H and Cl is added. This here does not require any rule, but in second time when you add H here, the double bond will become into single bond and you will get a carbocation with a Cl, right. So, this Cl will have a stabilization of this. First added Cl shows a stabilization, that is why second Cl again goes to here. So, hydrogen adds here and the Cl adds, therefore, you will get the 1,1 dichloroethane or gem type of the geminol or 1,1 dichloro, 1,1 dihalo compounds are formed. Now, the second example will be the X2. In the X2 addition, acetylene can be treated. X2 can be examples, can be chlorination, can be bromination. Chlorination directly, the chlorine gas can be taken, acetylene gas can be taken, added. But in the case of comparison, if you see, ethylene gas, chlorine gas without any catalyst reaction takes place. But here better to have some catalyst, that is anhydrous ferric chloride. If you add, then the reaction will become more. What is the role of this anhydrous ferric chloride? It holds the Cl minus temporarily. Okay, you will get the FeCl4 minus plus Cl plus. A clear electrophile, when it comes, the reaction will become easy. Otherwise, the alkynes, as I said, they are slow or sluggish. The reaction is slow. So, therefore, the catalyst, when you add, the reaction takes place. However, catalyst is not consumed. Either side 1,1 chlorine will be added. Second time it will be slightly better reaction because double bond it is. So, without any much catalyst problem, you will get tetrachloro product will be formed. These chlorinated products have got some industrial application. They are used as the tetrachloro, as well as when you use barium hydroxide, one HCl will be dropped, you will get a trichloro product. Both Vestrol and Vestrosol are used as a solvent, that is in the paint removing and all that, they are used as a solvents. But twice the addition takes place. First one Cl plus minus, another Cl plus, another minus. So, tetrachloro 1,1,2,2 tetrachloroethanes are formed. Now similarly you can take addition of HOX, where X can be again HOCl, you can take HOBr. These are all we have already verified with the alkenes. So let us have the similar reaction with HOCl, hypochlorous acid, HOCl. Okay. Then one side OH, Cl will be the plus here, electrophile, step 1, and then followed by the OH minus. So one side you will get a Cl, the other side OH will be added. Now the one more HOCl, second time one more HOCl is added. Here the Markovnikov rule fails because one hydrogen is there. So first attacking species is Cl. So this attacks on the chlorine, so that the carbocation is better stabilized by the 2p conjugation. This is pp conjugation, whereas here the chlorine is a 3p 2p. This overlapping requires a 2p 3p, whereas carbon oxygen is 2p 2p. Therefore oxygen can show better the mesomeric effect than the chlorine. So always Cl goes to this side, so that intermediate is formed on the carbocation where OH is there. So this stabilization is a better one than the stabilization through this chlorine mesomeric effect. So therefore 2 Cls will be added one side, 2 OHs will be added one side. However 2 OHs eliminate water. So finally what comes is a dichloro with one hydrogen, and aldehyde is formed. Dichloroacetaldehyde is formed. 2 Cl this side, 2 OH that side. But 2 OHs eliminate water, will become an aldehyde function. So dichloroacetaldehyde will be the final answer. Here first step no problem, Cl and OH will be added. While adding the second mole, the Markovnikov rule is not applicable. Add Cl plus here, you get carbocation here. Add Cl, if you add here, you get carbocation. Which carbocation is more stabilized is the criteria. The carbocation attached with OH shows a lone pair of the oxygen is 2p. Carbon is also 2p vacant orbital. So that overlapping will be 2p 2p overlapping we say. Instead if a Cl is added that side, you will get a carbocation where Cl is showing mesomeric effect, which belongs to a 3p series. Carbon is 2p, chlorine is 3p. So overlapping is not much perfect. Therefore we say 2p 2p overlapping is better. So carbocation formed on the OH containing carbon is better stabilized. That's why 2 OHs same side, 2 Cl same side we explain. Now addition of water, HOH addition, is also called hydration. Again we have a comparison here. Ethylene with water, actually no reaction, but ethylene, water and sulfuric acid there is a reaction. So ethylene itself needs a catalyst. So acetylene requires 2 catalysts. It is nothing wrong to justify, because ethylene doesn't require any catalyst for chlorination, but acetylene needs a catalyst because acetylene is slow reactive. So acetylene requires addition of water, 2 catalysts. One is concentrated H2SO4, another one is the mercuric sulfate HgSO4, mercuric sulfate and the sulfate. So the anion should not have a competition with the anion of the water. The anion present here either should be same anion or weaker than the anion of the reagent. That is the criteria here. So anion is OH minus, cation is H plus, is it? Anyhow, sulfuric acid proton first attacks, then the whole water attack. That is the electrophilic addition in the alkynes we have seen. First, what is the role of sulfuric acid? H plus first attacks, followed by the whole water attack, that H plus again given back. So the mercury makes a loose bond with the triple bond and try to polarize the triple bond. That is what the metal ion mercury is explained. Somehow 2 catalysts we are using. Catalyst 1 is sulfuric acid, another catalyst mercuric sulfate, both we are using with the water. The real reagent is however HOH. So one side H is added and the another side OH is added. This is the first mole addition. Now the second mole addition you can carry on with the same catalyst following the Markovnikov rule also, backed by the carbocation. H adds here, carbocation here, formed is by lone pair of the OH stabilized. Therefore, 2 OHs goes for the same carbon. This is what we explain. Markovnikov rule, or the concept of Markovnikov rule, is backed by the stabilization of the carbocation. This product will not have any stability. So, 2 OHs same side, eliminate water. So, you will get an aldehyde like this containing the 3 hal, that is acetaldehyde is formed. Or you too can have another phenomena. After adding the first mole, this compound is a enol. Enols undergo tautomerization. Tautomerism is allowed for the enols. So, hydrogen goes here, double bond comes here. So, in this way we are adding 2 waters, water plus of water and minus of water. 2 waters added, 1 water deleted. Net is 1 water only. Therefore, add 1 water and show the tautomerism. That is also equal product, same product is coming. So, you can show the mechanism this way, or add water then tautomerize it. Either way it is okay. Similar the case you can also extend in the propyne case also. When you add water, first water with the help of catalyst, no problem, follows Markovnikov rule and you will get the OH in the center. So, step 1 itself requires a Markovnikov rule. Actually, in the first step there is no Markovnikov rule, only second step. But now here, because here one hydrogen is there, no hydrogen. So, OH minus goes here, H plus goes here. First step itself Markovnikov rule. This you can add water, delete water, and directly you can show tautomerism directly. So, enol tautomerizes to give the acetone. So, propyne gives a propane, ethine gives a ethane, all aldehyde coming, but propyne will not give propane aldehyde, instead propanone coming. So, any XYZ group you can have here, like for example phenyl containing acetylene will give the phenyl containing ketone. You can generalize that whatever the phenyl you have, that phenyl will be resulted here, but this part will become into the ketone. You can have XYZ groups containing and goes on converting into this one. It's a beautiful conversion also. Alkyne into the directly into the methyl ketones are formed from the different types of the X or Y substituted alkynes. So, this is happens to be one of the important reaction also, because it is passing through the enol tautomerization and all that. So, addition of water, step 1 itself sometimes requires a Markovnikov rule, and then all that involvement makes this reaction little more important rather. So, let us take the next electrophilic addition, that is addition with sulfuric acid. Pure concentrated sulfuric acid at room temperature, it adds, does not require any catalyst. Acetylene adds sulfuric acid. Once the H and HSO4 will be added, this is called vinyl, this is sulfate. So, vinyl hydrogen sulfate, it is called vinyl hydrogen sulfate. This undergoes one more addition, again sulfuric acid will be added following the Markovnikov rule. So, you will get CH3CH. So, 2 sulfates, that is OSO3H and OSO3H. So, 2 sulfates are one side, one side methyl will be there. This is called ethylidene disulfates are formed. This compound has some application. When you heat it, you get back the again acetylene. This compound is unstable one. So, therefore, when you heat it, you will get back the acetylene, or you just add water, no heating at room temperature, just add water. The both sulfates are exchangeable with the water. So, 2 OHs will come. The 2 OHs is unstable one, eliminates water, you will get the acetaldehyde formation. So, one may also prepare the acetaldehyde by this way also. Take first acetylene, add sulfuric acid, concentrated sulfuric acid must be, and it is at room temperature, no heating, nothing. So, both the sides H and HSO4, H OH and HSO4 will be added. This ethylidene disulfate undergoes a pyrolytic type of breakage into acetylene back, or if you add water, a nucleophilic substitution reaction taking place, substituting the two sulfates. Sulfuric acid is one of the best outgoing group, that is was used in the tosylation followed by the halogenation reaction, one of the best outgoing group. So, it is an anion from the strong acid. So, it is a weak base, easily replaceable. So, the OH minus can conveniently replace the two sulfates and you will get two OHs. However, two OHs and the same carbon eliminates water, you will get the final compound will be the acetaldehyde is formed. So, the preparation of acetaldehyde from acetylene through this sulfonation also one can demonstrate. So, let us have the another electrophilic addition with acetic acid. Acetic acid has no electrophilic addition on the alkenes, but here the acetic acid also adds on the alkynes. Alkynes adds acetic acid in presence of a mercuric acetate Hg OCOCH3 taken twice. As I said just now, when you are adding acetic acid, anion is acetate anion, right? So, the anion part generally in the catalyst, same anion should be there or weaker than this one. The previous case when I add water, the OH minus is the anion. So, sulfate is the weaker than this. So, therefore, there is no competition. Here we have taken the same anion. You can take magnesium hydroxide, but there will be a confusion. When you are doing the chlorination, do the ferric chloride, not ferric bromide. When you are doing bromination, use the ferric bromide. Like that, same anion are weaker than that, there will not be any competition. So, acetate anion will be the group we are adding. So, one side hydrogen is added, one side acetate anion is added, OCOCH3. This is called a vinyl containing acetic acid. So, we call vinyl acetate, common name however. Systematically named as a, that is ethanoic acid containing ethanyl. Ethanyl ethanoate will be the systematic name. Once again it adds a, second time adds a, and once again this will become 2 hydrogen. So, CH3, this side you have a OCOCH3 and again OCOCH3. This is also ethylidene diacetate. So, 2 acetate anions one side following the Markovnikov rule, therefore, twice acetic acid adds. This compound has one industrial application. Around 600 degrees centigrade, when you heat it, it breaks into 2 compounds. One becomes into acetaldehyde, that is very useful product industrially. This side you will get a anhydride, acetic anhydride is formed. So, in fact, the acetic anhydride preparation from the acetic acid is commercially useful. Acetaldehyde is formed from the acetylene oxidation, acetaldehyde. Acetic acid dehydration, this is hydration, this is undergoing dehydration, water is exchanged in fact. So, both the conversion of acetylene to acetaldehyde, acetic acid to acetic anhydride, both are industrially the fetchable reaction. Therefore, here a mixture of acetylene and acetic acid is converted to a mixture of acetaldehyde and acetic anhydride, both are industrially useful. So, therefore, decomposition of this ethylidene diacetate gives a acetaldehyde and the acetic anhydride. This is acetaldehyde, another one is 2 products are formed, breaks into 2 pieces and then you will get anhydride and this acetic acid. Now, let us go for the second type of the reactions, that is oxidation of the alkynes. Alkynes can be oxidized with the alkaline KMnO4 . So, double bonds are with the alkaline KMnO4 known as Bayer's reagent. Bayer's reagent oxidizes the alkenes into the glycols. This is as a reference just I am quoting, and here we have a triple bond. Let us take some alkyl groups containing this one. So, the similar reaction you can expect here also. Permanganate MnO4 attacks and then converts slowly into the glycols by hydrolysis concept. So, here also 2 pi bonds are there. Therefore, you expect each pi bond is converted into this type of a glycol. 1 pi bond, 1 glycol. Another pi bond, another glycol. That is logically correct. And however, 2 OHs and the same compound, therefore, the compound gives finally into a ketone. A diketone is formed. There the reaction stops, in fact. That is what the alkaline KMnO4 converts into the diketone. 1,2 diketones come. However, another reagent we have acidic KMnO4. Acidic means here what is the medium means sulfuric acid, dilute sulfuric acid we explain. So, dilute H2SO4 if you have. The second step will be the common, this will be the common, and thereby even this will be the common. Up to this it is the common reaction. However, it further undergoes once again breakage because of the sulfuric acid effect. The oxidation step 1 gives the glycols, elimination of water gives the 1,2 diketones. This 1,2 diketones also undergo further breakage to give the 2 pieces of acids. So, we have here a comparison once again. Even a disubstituted alkenes or disubstituted alkynes, both will give the corresponding acids in the acidified KMnO4. If it is alkaline KMnO4, disubstituted will give glycols, disubstituted in the this case ketones are formed, right? Difference is there. But acidified KMnO4, both disubstituted alkenes and alkynes both cut into the triple bond, that is 2 acids are formed in the acidic medium. Alkaline KMnO4 acidic is slightly stronger oxidizing, therefore, an extra step taking place and then cut takes place, 2 acids are individual acids are formed depending upon the R groups. The oxidation with ozone is called ozenolysis. Ozenolysis also once again in alkynes we have 2 types of ozenolysis. Let us take some alkyl group containing acetylene is taken. Similar the case with the enes, here also a ozone molecule is consumed and then undergoes a rearrangement. Finally, what happens is a ozonoid is formed. The ozonoid will have like this structure. This is what a alkyne ozonoid. In the alkenes this bond will not be there, but here one bond is there. Now, this ozonoid dash ozonoid has got 2 types of the further reaction. One is only water, the other one is water with zinc. Water with zinc, when I use this nascent oxygen will go with the zinc forming the zinc oxide. So, the alkyne is converted to diketone. This is similar with the alkaline KMnO4 diketone comes. Reductive ozonolysis, this process step, first ozone then followed by this water addition is called reductive ozonolysis. Reductive ozonolysis. So, reductive ozonolysis will give zinc oxide and the diketone, 1,2 diketone, side by 2 ketones, 1,2 diketones are formed. Otherwise, only water is used. Here also this 1,2 diketones will come, but acidified KMnO4 cuts it like that. This diketones will cut and becomes into the acids. This is like a acidified KMnO4. So, oxidative ozonolysis, this type is called oxidative ozonolysis. Oxidative ozonolysis. So, in one way you can say reductive ozonolysis is equals with Bayer's reaction. Oxidative ozonolysis is equals to with the acidified potassium permanganate. So, the molecule becomes into 2 pieces and gives 2 individual acids. This is something same like in the acidified KMnO4, that is alkaline KMnO4, this is acidified KMnO4, equivalent. Reductive ozonolysis and alkaline KMnO4 Bayer's reagent will give same answer on provided the alkyl containing the alkynes. We have one more oxidation of acetylene with a chromic acid. Chromic acid is a very strong oxidizing agent prepared by the take dichromate, dissolve in water, aqueous solution, then add sulfuric acid. An aqueous solution is taken, that means water also will be there. All this combination is known as what? Chromic acid. In fact, this is a dichromate with water becomes chromic acid, and sulfuric acid will nullify. You will get first, the moment sulfuric acid is added, H2Cr2O7 will come. With this water it decomposes and forms into 2 moles of H2Cr2O8, H4. That means you will get H2Cr O4 taken twice. 2 moles of H2CrO4. This is called chromic acid. This chromic acid converts acetylene into acetic acid. Now, explanation is slightly difficult because one carbon undergone reduction, the other side carbon undergone oxidation. How it is possible? What type of mechanism must be? Actually, the mechanism takes place by addition of water, catalyzed by the acid. Addition of water, we know very well, HOH enol is formed, tautomerizes to give the acetaldehyde, right? So, acetaldehyde formation, we know that hydration in acidic medium, HOH enol, ethanol, vinyl alcohol, tautomerizes to acetaldehyde and mild oxidation. You can explain acetic acid formation. So, one side methyl, one side COH. So, acetylene on chromic acid, industrially it is possible to prepare or convert acetylene into acetic acid, in which it looks like this carbon is reduced, that carbon is oxidized, but actually it passes through the hydration followed by the mild oxidation to give the acetic acid. So, acetic acid has a sustainability because of the resonance stability and suppression of hyperconjugation. You will get that acetic acid will stay back in this chrome. However, perfect chromic acid, if you take, anything will be oxidized to carbon dioxide, but a level, one particular level of dilute chromic acid, if you use, acetylene can be converted into the acetic acid. Under the oxidation, we have a combustion reaction. In the combustion reaction, all organic compounds are converted into the, let us take CnH2n plus 2 or whatever it is, or minus 2, alkynes is minus 2 hydrogens. Whether it is plus 2 or minus 2, all are converted into the carbon dioxide or H2O. Alkanes, alkenes, alkynes, all are undergoes beautifully combustion to give this one, and a huge amount of energy is released. That is what all alkynes are used as a very good fuels, isn't it? Alkenes are alkynes, alkenes, all are used as fuels, but significantly if you use specifically, there is a difference, a fundamental difference. If you take methane, okay, if you take ethane, let us take CH3, you consume O2, gives the 2 moles of CO2 plus 6 hydrogen, therefore 3 H2O is formed, right? And whereas if ethylene you take, again O2 is consumed and you will get the 2 moles of carbon dioxide, which is common, but the H2O is only 4, so 2 H2O is formed. When you take acetylene, this is also oxidized with oxygen, you will get the again 2 moles of carbon dioxide, but water formation will be only 1 mole of H2O is formed, right? So, energy if you compare per mole, if you take 1 mole of ethane, 1 mole of ethylene if you take, the energy liberated in the case of acetylene will be less. The values are not correct exactly, around let us take around 325 kilocalories per mole. If I take this is around 275 and around 225. The values to be, actually I didn't remember exactly, but for the experimental value let us take like this, comparatives, which gives the more energy in the per molecule, means ethane giving the more energy, right? But acetylene molecule flame can be used to melt the metals, whereas alkane flame cannot. Maximum temperature released, this is energy I am talking. if I call in terms of the temperature released by alkanes will be around 1000, beyond 1000 you can't. But acetylene temperature produces around 3 to 4000 degrees centigrade, means most of the metals will melt with that temperature. So, huge amount of temperature it is coming, whereas in this case only below the 1000 it is coming. Though the amount is liberated in acetylene case less heat is liberated, but temperature is found to be more. Why? Means there are two differences. One is less water, this is the first reason, less H2O is formed. Each water molecule formed in the flame, water formed means it will be liquid, isn't it? So, liquid takes some energy and evaporates. So, the more the water formed, more evaporation requires more energy, wastage of energy will be there. This is one point. Second point is acetylene has a low flash point, means the temperature required to catch the fire in the case of acetylene is very low temperature. With low temperature itself it catches fire. In this case, unless you heat certain heat, the molecule will not turn up into that is burning reaction. So, therefore, low flash point and the less water molecules formation, acetylene though less amount is liberated per mole, the high temperature is released. That is why the acetylene is used in the welding purpose. So, two metals will be metal ends will be heated and joined, or metal can be cut by exposing this flame, it becomes liquid, therefore you can cut, just like two candles, one candle you can cut, or to join the candles by exposing to heat, they melt, isn't it? Immediately you can join. Like that the metals can be cut and joined, that process is called the welding purpose. So, acetylene gas is used in the welding purpose, because acetylene and oxygen cylinders will be used to get the 3 to 4000 degrees centigrade, which is easily melt the most of the metals. So, the combustion, all are giving combustion, no doubt, but acetylene combustion gives a high heat of the temperature, that is what it is used in the welding industry. So, the next property of the alkynes is polymerization. As I said, the sp hybridization of acetylene, the electrons are more tightly held, therefore, even the polymerization is also polyacetylene formation. Industrially, the polyacetylene formation is not that favorable reaction. Instead, a low level polymerization we have. Acetylene can be polymerized into the 3 low level polymerization. The first one is trimerization. First you take dimerization, otherwise dimerization, that means two molecules are joined together. So, one acetylene is joined to another acetylene, this is what dimerization. One acetylene adds on another acetylene. So, you break the acetylene into plus minus and add it on another acetylene, you get this type of the. So, this time one hydrogen will become 2 hydrogen. So, one H is added. So, this side you will get this CH. So, this is what one acetylene added on the another acetylene is called dimerization. This can be done with nickel cyanide. When you add nickel cyanide, it undergoes dimerization. Instead, if you pass through the red hot copper or iron tubes, so when you heat it, actually it catches fire. With that fire, metals will be melt. So, therefore, let us not allow to undergo combustion reaction. You take a iron tube and make it red hot, then pass this acetylene gas. Inside there is no air, oxygen will not be there, therefore, combustion will not take place, but the catalytic activity of this copper and the iron will make the acetylene to trimerize. So, this process is called trimerization. Trimerization and cyclization also. So, instead of 3 straight members, 3 acetylenes are joined to get the cyclic 3, that is 3 acetylenes are joined. This is nothing but the benzene. It is a very good aromatic compound. So, because of the aromatic stability, the formation of benzene will be very easy. Instead, you too can find a tetramerization. Tetramerization, this is also cyclization. I think nickel cyanide is better used for here. And use here as a copper chloride and copper acetylide, CuC2, and a copper chloride, or ammonium chloride also works well. Take copper chloride and ammonium chloride. Copper chloride, ammonium chloride mixture for the dimerization. Red hot iron tubes for the trimerization. Nickel cyanide for the tetramerization. In the tetramerization, 4 acetylene molecules join together to get a ring, which is very much close benzene, but it is a non-aromatic compound. Non-aromatic, look like anti-aromatic, but the molecule exists like a non-planar models. So that's why the molecule shows a non-aromatic property. It's a non-aromatic. You may call it as a cyclooctatetraene. Is a tetraene, 4 enes are there, and 1, 3, 5, 7 also you can fix. 1, 3, 5, 7 cyclooctatetraene is formed, which is a non-aromatic compound. This is the polymerization, actual real polymerization. Can also, acetylene will use polyacetylene, leaving some alkenes in the polymer, but that is not industrially fetchable, and these 3 low level the polymerizations are more easy rather than, because of the less reactivity of the acetylene probably.